Hi everyone, my name is Azri. I'm a research fellow at the University of Surrey. Today I'm going to present our paper on tracking sound sources for object-based spatial audio in 3D audiovisual production. This is the outline of this presentation. I will first give an introduction which covers the motivation of the work and our contributions. Then I will explain our model and the proposed method for audiovisual sound source tracking. After that, I will proceed with the experimental evaluation and finally conclude our paper. Introduction. In immersive and interactive audiovisual content, there is very significant scope for spatial misalignment between the two main modalities, audio and visual. So in production that have both 3D video and spatial audio, the positioning of sound sources relative to the visual display requires careful attention. This may be achieved in the form of object-based audio, moreover allowing the producer to maintain control over individual element within the mix and also enabling the greatest flexibility in adapting a scene to the local reproduction system and the user's preferences. Each audio object contains metadata describing essential attributes and properties such as its position over time throughout the scene. As a result, tracking of sound sources needs to be performed for automated positional metadata extraction. In this work, we focus on tracking sound sources in 3D audiovisual production. This is our audiovisual array used for capturing the 3D audiovisual content, consisting of 16-element microphone array and 11-element light field camera array. The main purpose of having the camera array is to capture the visual depth, but in this work we also utilize the camera array for sound source tracking together with the microphone array. The audio and visual cues both have their own benefits and drawbacks. Visual cues are generally reliable and accurate. However, the tracking area is limited, the performance is limited by occlusion and sensitive to change in illumination. Meanwhile, audio tracking is not restricted by this limitation. Therefore, fusing both audio and visual information can provide more robust tracking performance as both modalities complement each other. There have been several audio visual tracker proposed, including those that operate in the 3D space. In one, a 3D single speaker tracker was developed, and to fuse audio and visual cues, an adaptive particle filter was proposed based on the audio-visual reliabilities. Two presented a new vision strategy based on particle filtering for multiple speaker tracking. However, it was developed under the assumption that the number of speakers is known and constant. In a 3D multiple speaker tracker using the probability hypothesis density, P.H.D, filtering approach was proposed for tracking unknown and variable number of speakers. Instead of fusing data from the two modalities in P.H.D filtering, only the visual data was filtered and the audio part was fused later after P.H.D filtering to compensate for misdetection in the visual tracking results. Hence, the contribution from the audio part was limited, and it was on the assumption that all targets are visually detected. Against this background, we introduced a 3D multiple sound sources tracking system relying on the fusion of audio and visual modalities using the P.H.D filtering framework. As opposed to the tracker in 3, the fusion is performed within the P.H.D filter and hence allowing flexibility on specifying the weight or the significance of the audio information. Our tracker is called the 3D AVI P.H.D tracker. The P.H.D filter is modified to exploit the reliability from both audio and visual data. Finally, we apply the proposed 3D AVI P.H.D tracker to track sound sources in 6DOF VR production. Next, we proceed to the system model. In order to automatically extract the metadata and produce audio objects, our proposed solution relies on these three main processes. First is sound source tracking, and the result from the tracker is used for beamforming, which will generate a set of reference signal. This reference signal will then be used in associating the high quality audio signals from the closed microphones with the correct metadata. In this work, we focus on the first process, which is sound source tracking. As you can see in the diagram, our tracker consists of three main components. The first two components process the audio and visual data independently. Then the 3D position from both audio and visual processing are fused using the IPHD filter. The reliability values are exploited to produce more accurate and robust 3D position estimates. At the output of the tracker, we will get the final estimate for the 3D sound source position plus the corresponding ID for the target. The SRP-FET method is among the commonly used method for acoustic source localization due to its robustness, especially in a noisy and reverberant environment. However, the SRP computation is based on intensive grid search method to find the global maximum, and it is computationally expensive, especially for the 3D search space. Therefore, we employ the low complexity SRP FET SRC for stochastic region contraction method in our system. In the case of multiple sound sources, we use the region zeroing approach with the SRP FET SRC method. Visual processing. Here, our goal is to detect and track the sound source location from the visual input. We employ OpenPose to detect the 2D skeletal key point of human subjects in the video streams. Due to the skeletal structure of the OpenPose, we use the nose joint and assume there is a negligible offset between the nose and the mouth. Due to the inconsistency of the 2D detection provided by the OpenPose, 2D detection must be sorted such that they are spatially consistent between the camera views and temporally consistent over time. And to do that, we utilize the detection sorting algorithm in 7. The sorted 2D detection are combined with confidence to remove the impact of potentially unreliable detection to estimate the 3D location via triangulation. Both positional data from audio and visual processing are fused using the IPHD filter. On top of using the two modalities, PHD filtering also can mitigate outliers and smooth the source trajectories from noisy data. There are several steps involved in IPHD filtering. Start with the prediction step. Several iteration updates depend on the number of sensors considered. In our case, we first update with the audio observation and then re-update with the visual observation. After that, we have the resampling step, state estimation step, and finally, we assign ID to the final 3D position estimate. We modify the prediction and update steps to utilize the reliabilities from both modalities. As being mentioned, we perform 2 times the update step, and since the tracking performance depends on the order of the sensor update, we start the iterated update with the less reliable data, which is the audio data, and then followed by the visual data. The capture of the 6DOF VR content was done using our audiovisual sensing platform, consisting of 11-element light field camera array and 16-element microphone array. On top of this, we had 2 spot microphone and an ambisonic microphone to record high-quality audio. But for sound source tracking, we only relies on the microphone array. There were 2 subjects in the captured scene, standing side by side with little movement from where they stand. The duration of the sequence was 20 seconds. The 3D position of both speakers were estimated using our tracker, and to evaluate the performance, ground truth was established by using visual detection and tracking from 2 separately positioned audio-visual sensing platforms and by manually annotating the voice activity throughout the sequence. The evaluation was done on the spherical coordinate system where an estimate was considered to be valid if it's within plus minus 5 degree in azimuth, plus minus 10 degree in elevation, and plus minus 0.7 meter in radius from the ground truth. Here are the results from both separate audio and visual processing. 2 tracks from visual processing correspond to the position of the 2 subjects throughout the sequence, even when they did not speak. There was some detection missing, as can be seen from frame number 124 until 158 for speaker 1. This misdetection occurred when speaker 1 turned his face away from the camera. The recalls for audio and visual processing are 0.814 and 0.906 respectively, whereas the position for audio and visual processing are 0.883 and 1.0 respectively. In both metrics, visual processing outperforms audio processing, which is expected. It is worth noting that audio processing has better accuracy in azimuth direction than other direction, and this is due to the arrangement of our microphone array that has more microphones in the horizontal direction. Here is the result of the PhD filtering. Despite the small number of outliers introduced, which labeled as ID3 and ID4, we found that there is no misframe in both ID that are associated with our two subject ID1 and ID2 and achieve a recall score of 1. The audio information successfully compensated the misdetection from visual detection. We benchmark our 3D AVI PhD tracker with the visual-only 3D VI PhD, and the results are shown here. We can observe that the 3D AVI PhD tracker has better recall performance over the visual-only 3D VI PhD tracker. The lower precision value with the proposed tracker is due to the small number of outliers introduced in ID3 and ID4, which is not particularly an issue in our application, as the outliers will automatically be removed in the later stage when associating the metadata with the audio signal. Therefore, the priority is always recall over precision. In conclusion, we have proposed the 3D AVI PhD tracker relies on the fusion of audio and visual modalities using the PhD filtering framework. We have applied the proposed tracker for tracking audio object in 6 DOF VR production. Experimental results have shown that the audio information can successfully compensate the misdetection from visual-only tracking, as recall went from 91% to 100%, and hence demonstrating the effectiveness of the proposed tracker in fusing audio and visual information. As we show, the proposed tracker may be applied to more challenging scenarios, such as involving more movement of different types of object, and also scenario where some of the objects are located outside the camera's field of view. Benchmarking may be done with other state-of-the-art methods. This research was supported by the Innovate UK via the Polymersive Immersive Video Production Tools for Studio and Live Events project. If you have any question, you can also contact us through the email addresses shown on the slide. Thank you.